Okay, so let's unpack this a bit. Think about the buildings we spend most of our lives in, right? They're designed to be really sealed up tight, keep the outside world out. But what if that very efficiency, that tightness, actually created a hidden vulnerability? A quiet threat maybe lurking in the walls, under floors, something as common as, well, moisture. And what if this isn't just, a minor annoyance, but a silent, really potent force causing billions in damage, rotting buildings from the inside out, and maybe even making us sick?
Yeah, it's a huge issue.
So today we're doing a deep dive into the source material you've shared with us. We've got articles, research papers, notes, all covering this hidden science of moisture in buildings, and also the cutting-edge tech that's coming out to fight it, and this kind of revolutionary shift towards, well, truly resilient construction.
Right. And our mission here is really to pull out the core insights from all this information. We want to help you understand this complex, often invisible problem, grasp the real scale of its impact, both human and economic, and understand why it's becoming even more critical now, and see the powerful tech solutions that are honestly changing everything.
Yeah, get ready, because there are some facts in here that genuinely surprised us. Like just how much this seemingly small issue costs globally, or how that big push for energy-efficient design kind of inadvertently opened the door to, well, whole new kinds of problems.
Yeah.
This is a deep dive into the hidden world inside your walls.
Okay, so let's start with what the sources really highlight as the core conflict, what they're calling the paradox. See, over the last few decades, the big drive for energy efficiency led us to build these incredibly airtight, really heavily insulated buildings.
Which, sounds like a good thing, right, on the surface. Tighter buildings mean less heat loss, maybe lower energy bills.
Oh, absolutely. They are fantastic for thermal performance, yeah. They keep the warmth in winter, the cool in summer, way better than older buildings. But the paradox is they've kind of lost what those older, leakier buildings had going for them naturally, like a forgiveness factor. Those drafty old places might have used tons of energy, but air moving constantly through cracks and gaps helped them dry out passively if moisture got inside. Modern, sealed buildings, they just don't have that luxury.
Ah, okay. So any moisture that does manage to get inside is basically trapped.
Exactly. They have very little, natural ability to buffer or dry out moisture. So if there's even a small flaw somewhere in the construction, maybe a leaky pipe or just uncontrolled water source inside, that moisture just can't get out easily. It builds up and the damage happens much faster and, frankly, on a larger scale than it would in an older building. It makes precise moisture management absolutely essential, not just a nice to have anymore.
Right, that makes total sense. So, okay, if the building is sealed tight, how does moisture actually, breach this airtight barrier? What are the ways it gets in?
Well, the sources break down the main pathways. The most obvious one is bulk water intrusion, so direct leakage. That's rain getting in through a poorly sealed window, maybe groundwater seeping through a basement wall.
Like a hole in your roof, basically. Simple leak.
Pretty much, yeah. Then there's something called capillary action. Think of materials like concrete or brick. They act a bit like sponges. They can actually wick liquid water upwards through tiny pores, sometimes even against gravity.
Okay, right. Like how a paper towel soaks up a spill on the counter.
Exactly. That's a good way to think about it. Another big one is air infiltration. This is where air currents, maybe driven by wind or just the stack effect in a building, literally carry water vapor along with them through any tiny gap or crack in the building envelope. Around pipes, wires, any little opening where it's not perfectly sealed. And finally, there's vapor diffusion. This one's slower, but water vapor can actually move directly through building materials themselves. It's driven by differences in humidity, inside versus outside, or warm side to cold side.
Wow, okay. So it sounds like controlling the building envelope, that sort of outer skin of the building, is just absolutely critical.
It really is. It's the primary defense layer. The sources are super clear on this. Failure of the building envelope is a leading cause, maybe the leading cause, of premature building damage and performance issues.
This sounds incredibly complicated to actually predict and control, though. It's not just about slapping some sealant on, is it?
Oh, not at all. This is where we get into the real science of it. The source material really emphasizes what's called hygrothermal analysis. That's the study of how heat and moisture interact and move together within a building structure. You have to understand things like relative humidity or RH.
RH, right? That's like how muggy the air feels, how much water vapor is in the air compared to how much it could hold at that specific temperature.
Exactly that. And understanding how that RH relates to the temperature, and crucially, the dew point. That's the temperature where the air gets saturated and water vapor actually condenses back into liquid water, like on a cold glass in summer. Psychrometry is the specific science focused on managing all these together, temperature, humidity, airflow especially, to control that condensation and also speed up drying if things do get wet. And with modern walls and roofs having so many different layers, different materials, the old simple rules of thumb, they just don't cut it anymore.
Now, how do designers actually figure this stuff out for these really complex buildings then?
Well, they rely heavily on sophisticated computer modeling now, software like WFI, for example. These tools can simulate how a particular wall or roof assembly will perform over, say, years in a specific climate. They can predict where moisture problems might pop up before a single thing is even built. It's really about science informing the design up front.
And obviously, the weather outside plays a huge role in all this.
Oh, a massive role, and one that's becoming more and more significant, unfortunately. The sources directly link this increased moisture risk to the effects of climate change. We're seeing more intense rainfall, higher winds, elevated background humidity in many areas. These more extreme conditions put way more stress on building envelopes, making them more likely to fail. It means we really have to design and build with a forward-looking perspective, anticipating tougher conditions down the road.
Okay, so we've got these tighter buildings, complex physics at play, and worsening weather creating the sort of perfect storm for moisture problems. But what are the tangible impacts? What happens when moisture really takes hold? What are the real-world consequences?
Well, the consequences are severe, unfortunately, and they hit two major areas really hard: human health and the economy.
Let's talk health first. That feels incredibly important, especially given how much time we all spend indoors these days.
It's absolutely critical, yeah. When you have persistent dampness, constant moisture, you're basically creating a perfect breeding ground for mold and bacteria. And this directly degrades your indoor air quality, or MEAQ, and that has direct health consequences for people living or working there.
Okay, what sort of health problems are we actually talking about? Are they clearly linked to damp indoor environments?
Oh yeah, the link is very well established. Health organizations like the World Health Organization, they're clear on this. The sources detail a whole range of respiratory issues. It can actually cause asthma to develop, particularly in children, or make existing asthma much, much worse. It's linked to allergic rhinitis, hay fever symptoms, shortness of breath, wheezing, coughing, and just generally an increased risk of respiratory infections. And in some sensitive individuals, it can even lead to a really serious lung condition called hypersensitivity pneumonitis.
Wow. That sounds like a serious threat just from, dampness.
It is, and the sources bring home the most tragic potential outcome with a really stark reminder. The case of that little boy, Owabi Shak, in the UK a few years back, he was only 2, and he died from a severe respiratory condition that was directly caused by prolonged exposure to mold in his family's flat. It's just a heartbreaking example of how grave the consequences can potentially be.
Gosh, yeah. It really puts it in perspective.
And beyond those really clear respiratory links, there's also, evidence suggesting connections between damp indoor environments and symptoms often lumped together as sick building syndrome. Things like persistent fatigue, difficulty concentrating, even mood disorders.
Didn't the sources mention something about cognitive function too? I found that fascinating.
Yes, that's a really powerful point. There was a study from the Harvard Chan School of Public Health. It showed that workers in office environments with better indoor air quality, which is often linked to proper moisture and ventilation control, they scored remarkably, like 61% higher on cognitive function tests. So it's not just about being comfortable. It can actually impact how clearly we think and how well we perform our jobs.
And I imagine some people are maybe more at risk than others?
Definitely. Children, the elderly, and really anyone with pre-existing respiratory conditions or a compromised immune system, they're particularly vulnerable. This really highlights why controlling moisture and mold is just absolutely non-negotiable in places like schools, hospitals, aged care facilities. And the medical community is increasingly recognizing this. They're even establishing specific clinical pathways now for doctors to help patients who present with symptoms that might be linked to exposure to biotoxins from damp buildings.
Okay, so the health case is undeniable and potentially severe. What about the financial side? What's the economic cost of letting moisture run rampant?
It's staggering. Honestly, billions and billions of dollars. The sources quantify this in a few different ways. You've got the direct costs. Buildings basically falling apart prematurely because of rot, corrosion, finishes just deteriorating. During construction itself, if materials like timber or insulation get wet on site before they're properly installed and protected, they can be ruined. That causes huge delays, expensive replacements. And then inside the finished building, Water intrusion can destroy valuable inventory, sensitive equipment, you name it.
I bet insurance companies know all about this problem.
Oh, they absolutely do. Water damage is actually a leading cause of loss in the construction industry. Something like nearly a third of all contractor liability claims are related to it. And for homeowners, the average water damage insurance claim back in 2021 was over $12,500. And get this number, just 1 inch of floodwater in a typical home can cause around $25,000 worth of damage.
1 inch. That's unbelievable. It really drives home how quickly these costs can escalate, doesn't it?
Yeah, and on a national scale, the numbers are just immense. American businesses, for instance, spend an estimated $9 billion every single year on repairs and litigation that stem directly from moisture problems. And then you have to add the health costs on top
Wow.
of that, maybe around $3.5 billion annually, just in asthma-related medical costs linked back to damp and moldy environments.
Wow. This makes the argument for being proactive, doing something before disaster strikes instead of just waiting for it.
Yeah.
It seems incredibly strong.
It's really the core economic takeaway from all the source material. Prevention is vastly, vastly more cost-effective. Unplanned, reactive maintenance fixing things after they break is typically something like 3 times more expensive than planned, proactive work. And those reactive costs aren't just the repair itself, right? It includes scrambling for materials at premium prices, overtime labor, and critically, the cost of downtime and business interruption. That can be huge for businesses. There are studies looking at adapting infrastructure for climate change, and then they show that investing proactively saves billions down the road. That same logic applies directly to buildings. Pay a little now, invest in prevention, to avoid paying a fortune later.
And there's an environmental cost, too, isn't there? All those damaged materials, they just end up in landfills.
Yes, absolutely. And another key point that often gets missed, moisture-damaged insulation. It loses its R value, its effectiveness.
So the building isn't actually insulated properly anymore. It's leaking energy.
Correct. Which means it uses more energy for heating and cooling, leading directly to higher utility bills and an increased carbon footprint. So early detection, preventing that insulation from getting wet, avoids that material waste and that hidden energy penalty.
Okay, so the problem's clear. The costs are enormous. Both human and financial and modern building, they're particularly susceptible. The sources also dig into some really interesting specific challenges in more advanced construction types. Tell us about mass timber and passive house in this context.
Yeah, these are great examples because they're both innovations aimed squarely at sustainability and energy efficiency, but they introduce their own specific moisture vulnerabilities that absolutely need careful management.
Okay, let's start with mass timber. It's getting a lot of buzz, seen as a green alternative to concrete and steel, really growing in popularity. Why is moisture such a critical issue for it?
Well, mass timber, things like cross-laminated timber or CLT, it's made from wood, right? It's renewable, it stores carbon, it has fantastic structural properties. But being an organic material, its fundamental Achilles heel, if you like, is moisture.
And I heard the biggest risk is actually during the construction phase.
Absolutely, that's a critical window. Unlike pouring concrete or erecting steel frames, these large mass timber panels are often exposed to the elements rain, snow on the construction site during assembly. If that timber absorbs too much moisture before the building is properly closed in, it can cause significant problems. You get aesthetic issues like staining that's really hard to get rid of, dimensional changes the wood swells, which can mess up critical connections and compromise the structure. And most seriously, it can create conditions for fungal growth and rot, which directly compromises the timber's strength and long-term durability.
So you can't just use a sort of standard generic moisture plan for these projects.
No, definitely not. The sources really stress that mass timber requires a highly specific, tailored moisture management plan. It needs to be developed right from the early design phase and then followed meticulously on site. There are resources out there, like the RDH Guide mentioned, that provide specific methodologies for doing that risk assessment and then verifying performance during construction.
This must fundamentally change how builders have to approach these projects, right?
It absolutely does. The whole industry conversation is kind of shifting. It's moving from just how do we build with wood to how do we prove definitively that we kept the wood dry throughout the process. This makes detailed monitoring and verification almost a non-negotiable requirement for these projects to be successful, insurable, and for owners to have confidence.
Are there design strategies that can help mitigate this risk?
Yes, hygrothermal research is providing some key insights here. For instance, studies are showing that CLT walls designed with exterior insulation layers tend to perform better. That insulation keeps the structural timber itself warmer and drier, reducing the risk of condensation happening within the wall assembly. And also, embedding sensors within the timber elements themselves is becoming seen as really essential for long-term monitoring of its moisture content, providing that crucial proof point over time.
Okay, that makes a lot of sense for a material like wood. Now, what about passive house? This is seen as the peak of energy efficiency, known for being incredibly airtight. How on earth does moisture become a problem in a building designed specifically to be so sealed off from the outside?
Yeah, this is what the sources refer to as the passive house paradox. The standard demands extreme levels of airtightness, often something like 8 to 10 times tighter than standard building codes. Now, this is brilliant for stopping uncontrolled air leakage and heat loss, and it does keep exterior moisture like wind-driven rain out very effectively. But it also means that moisture generated inside the building from people, cooking, showers, plants, has essentially nowhere to go naturally.
Right, just normal living generates moisture? Breathing even.
Exactly. All that normal daily activity creates water vapor inside. In a leaky old building, a lot of that just finds its way out through drafts. In an airtight passive house, it gets trapped, and this trapped moisture must be actively removed, usually by the ventilation system. Otherwise, internal humidity levels will climb, leading to condensation, especially on cold surfaces like windows or, more worryingly, hidden inside wall cavities, and eventually, mold growth.
So achieving that level of airtightness must be incredibly challenging for builders.
Oh, it requires exceptional attention to detail during construction. You need specialized sealing tapes and membranes, meticulous application, and rigorous quality control, including things like blower door tests at multiple stages to actually measure the airtightness achieved. And that combination of very high insulation levels plus that extreme airtightness actually increases the risk of condensation happening within the wall or roof layers, what's called interstitial condensation, if any water vapor does manage to get in or move into those colder outer layers of the assembly.
So the ventilation system isn't just about bringing in fresh air anymore. It's doing double duty as the main moisture control system.
It becomes the primary moisture management system, certainly for internally generated moisture. That's why the choice between using an HRV, a heat recovery ventilator, which tends to expel moist air along with stale air, or an ERV, an energy recovery ventilator, which recovers some moisture to help manage indoor humidity. Especially in very dry climates, that choice becomes a really crucial climate-specific design decision. Get it wrong, and you could end up with mold problems from too much humidity or discomfort and static from air that's too dry.
And the sources mentioned a specific case study highlighting this challenge.
Yes, they pointed to the example of 425 Grand Concourse, which is a large multifamily passive house project. With a high density of occupants all generating internal moisture from cooking, bathing, breathing, the standard ERV system, while very energy efficient, apparently wasn't quite sufficient on its own to keep humidity levels down, especially during cold winters. They actually had to add supplemental in-wall dehumidification systems. This really highlights that even with perfect airtightness and a well-designed ventilation system, managing the internal moisture load in modern, densely occupied buildings requires really sophisticated analysis and sometimes going beyond standard off-the-shelf solutions. It just underscores that when you seal the envelope that tightly, the mechanical ventilation system carries almost the entire burden for moisture removal.
Wow. Okay, these are clearly complex challenges with really high stakes involved. It definitely sounds like we need something more sophisticated than just traditional building methods or visual inspections. Is this where technology really starts to play a major role?
Absolutely. This is where the shift towards proactive management really takes off, enabled by technology. Tech gives us the tools not just to react, but to measure, understand, and even predict moisture issues before they escalate into disasters. And it's really built on this growing ecosystem of sensors, connected through the Internet of Things or IoT, and increasingly analyzed using artificial intelligence, AI.
So sensors are kind of like the building's nervous system then, feeding it constant information about conditions.
That's a great way to think about it, yeah. They essentially turn abstract environmental conditions like humidity or material wetness into measurable, actionable data. The sources survey several different types. You've got your ambient sensors, like thermohygrometers, which measure the temperature and relative humidity in the air. That's crucial for calculating things like dew point and condensation risk. Then you have embedded material sensors. These use various technologies, electrical resistance, capacitance, optical methods, and they're actually placed inside building materials. So within mass timber elements or inside wall or roof cavities to measure the actual moisture content of the material itself. You also have simpler leak detectors, often single-purpose sensors, just designed to give an immediate alert if bulk water is present, say, in a basement near a water heater or under plumbing fixtures. Some can even trigger an automatic shutoff valve to stop the flow. And then there are more advanced, specialized sensors for very specific applications, but the core idea across all of them is turning physical conditions into data points we can use.
And all these different sensors are connected somehow.
Yes, typically they're connected via IoT-enabled data loggers. These little devices collect the readings and then transmit them wirelessly, often to a cloud platform. And sensor technology itself is rapidly evolving, getting smaller, more accurate, using less power, which makes deploying them more widely much easier and more cost-effective than it used to be.
Okay, so you've got all this data flowing in from potentially hundreds of sensors across a building. How do you make sense of it all? How does it actually become smart?
Right, collecting the data is just the first step. The real power comes from analyzing it. This is where you see the convergence of IOP, that's the network collecting the data, AI and machine learning acting as the brain to analyze it, and often integrating with the building's existing management systems, like the BMS that controls the HVAC. This integration is what enables the big shift from purely reactive maintenance to truly predictive maintenance.
So instead of just reacting when a pipe bursts and water is everywhere, the system could potentially flag that a pipe is maybe at high risk of freezing based on temperature trends, or that a wall cavity is slowly getting damper over time, long before you'd ever see a visible stain.
Precisely. The AI algorithms analyze that continuous, real-time data stream. They're looking for patterns, subtle anomalies, deviations from normal baseline conditions that indicate a potential problem is developing before it actually causes a failure or visible damage. This can prevent incredibly costly unplanned downtime. It helps extend the lifespan of building components, and crucially, it prevents secondary damage like mold growth following a slow leak.
Are there real-world examples of systems like this in action already?
Yes, definitely. The sources mention specific systems, like Sensor Innovation's Into-Control system, which uses a form of hybrid AI to get predictive insights specifically from embedded moisture sensors in building structures. And you look at iconic smart buildings like the Edge in Amsterdam. It was designed from the ground up with a vast network of sensors feeding into an intelligent building management system to optimize absolutely everything from energy use to lighting to occupant comfort, all based on real-time data.
And what about this digital twin technology? How does that fit into the picture?
The digital twin. It's essentially a highly sophisticated, data-rich, often photorealistic 3D virtual replica of the physical building. The key thing is that it's constantly updated with real-time data flowing in from all those sensors in the actual building. This allows building owners and facility managers to visualize the building's performance in incredible detail, remotely diagnose potential issues without having to physically inspect every corner, check compliance against design standards or energy targets, and even run what-if simulations, like what happens to the condensation risk in this wall assembly if we change the insulation type, or how would a heat wave impact internal temperatures?
Wow, okay. This sounds like it makes really complex building science much more accessible to people who aren't necessarily, PhD-level building physicists.
That's a really key point the sources emphasize. The AI can perform the complex hygrothermal analysis or spot the subtle anomalies that a human might miss. And the digital twin presents those findings visually, intuitively, accessibly. It essentially democratizes building science insights, making them available not just to highly specialized engineers, but potentially to facility managers, building owners, maybe even restoration professionals trying to understand a situation.
And speaking of restoration, it's not just about preventing problems in new or existing buildings, right? This technology is also fundamentally changing how we deal with moisture damage after something has already gone wrong in the restoration industry.
Absolutely. The sources describe this as nothing short of a restoration renaissance. It's transforming the entire field, moving it away from sometimes subjective methods or just relying on experience towards a much more scientific, data-driven, verifiable process.
Okay, how does that work in practice?
Well, it really starts with applying the science of psychrometry properly. That means using the interplay of humidity, airflow, and temperature, sometimes called HT, in a really controlled way to create the optimal conditions for drying out wet materials effectively but also safely. The whole methodology becomes evidence-based. First, you do a much more thorough assessment using advanced tools, not just visual inspection, but digital moisture meters, thermal imaging cameras, and increasingly deploying temporary sensors to precisely map where the moisture is, how far it's migrated into materials, and how wet those materials actually are.
So you get a much clearer picture of exactly what you're dealing with from the start.
Exactly. Then comes the controlled drying phase. This involves using specialized equipment, not just blasting fans everywhere, but specific types of air movers, high-efficiency dehumidifiers like LGR, low-grain refrigerant, or desiccant units, sometimes even applying targeted heat, all carefully managed to maximize the rate of evaporation from wet materials, while critically preventing secondary damage, like causing wood to warp or crack from drying too quickly or unevenly. And then the crucial final step is verification.
Proving that it's actually dry, according to recognized standards.
Yes, exactly. It involves continuous monitoring throughout the drying process, using moisture meters, RH sensors, tracking the data to see the progress, and ensuring that the affected materials are returned to the established dry standard, typically defined by industry guidelines like the IICRC S500 standard before you remove the equipment and declare the job done.
And where does IoT technology, those connected sensors, fit into this process for the restoration companies themselves?
That's the real game changer for their actual business model. Using IoT sensors for remote monitoring allows restoration teams to track the drying progress on multiple job sites, 247, without needing to physically be there all the time. This significantly cuts down on the number of labor-intensive site visits, what they often call call-outs, just to take readings. It automates the data collection needed for reporting to insurance companies and clients, and in some cases, it even allows for remote adjustments of the drying equipment settings based on the real-time data coming in.
So they can operate much more efficiently, handle more jobs.
Massively more efficiently. It cuts down on labor costs, reduces travel time and fuel expenses, increases overall operational efficiency, and allows skilled technicians to manage a larger portfolio of jobs simultaneously. It fundamentally shifts the value proposition they offer. It moves away from just providing physical labor and equipment on site towards providing a more sophisticated, tech-enabled, data-driven service.
And the data itself becomes a huge benefit, I imagine.
Oh, it's invaluable. That continuous stream of data provides an objective, often indisputable record of the entire drying process, how wet it was, how conditions were managed, how long it took, and proof that it met the dry standard. This is essential documentation for clients, but absolutely critical for insurance claims. It helps streamline the claims process, minimizes disputes over the scope or effectiveness of the work. The sources really point out that the competitive edge in restoration is rapidly moving away from simply who has the most fans and dehumidifiers towards who has the best data, the best technology, and the expertise to use it effectively. And this also opens up doors to offering new types of services, like ongoing post-remediation monitoring to ensure the problem doesn't return, or integrating their services into a building's overall proactive maintenance plan.
Okay, it really sounds like this whole proactive, data-driven approach using technology offers significant benefits to pretty much everyone involved across the entire building lifecycle. Who are the key beneficiaries here? How does this value break down?
Yeah, the sources make a really compelling case for value right across the board. It's not just one group benefiting.
Let's think about facility managers first. The people responsible for keeping buildings running day to day. What's the payoff for them in implementing these kinds of technologies?
Okay, for facility managers, it's fundamentally about two things: protecting the physical asset they're responsible for and ensuring smooth, uninterrupted operations. That 247 monitoring acts like a silent watchman, protecting against potentially catastrophic losses from major leaks or floods. This is especially critical in buildings that house high-value inventory, irreplaceable items, or critical infrastructure like data centers or hospitals, where any downtime can cost literally thousands of dollars per minute.
Right. And that predictive maintenance capability means fewer nasty surprises.
Exactly. Being able to identify potential issues before they cause system failures or significant damage translates directly into less unplanned downtime, more predictable operations, better resource planning, and often much faster resolution times when an issue does arise because you know about it sooner. The sources mention potential improvements in response time of like 30 to 50%. It really moves them away from constantly reacting and firefighting towards more strategic asset management. They can use the data to optimize everything from energy consumption by the HVAC system to planning preventative maintenance schedules based on actual conditions, not just the calendar. Ultimately, it brings what one source cleverly called peace of mind, or POM, just knowing the building is constantly monitored and potential problems are being flagged early.
Okay, what about the designers and builders, the people who actually create these structures in the first place? How do they benefit from thinking proactively about moisture and maybe incorporating this tech?
Well, for them, it's largely about de-risking increasingly complex and innovative designs and also providing robust liability protection. Modern buildings are complicated systems, and the financial risk associated with construction defects leading to expensive moisture damage claims later on is really high. A building designed and built with integrated monitoring provides a verifiable data record. It proves that the design performed as intended, that the construction met quality standards regarding moisture. This offers powerful evidence against potential future defect claims years down the line.
This must be particularly relevant for those mass timber projects we discussed, given their inherent vulnerability.
Oh, absolutely essential for mass timber. Embedded sensors and ongoing monitoring provide that critical validation of the timber's long-term performance and durability. It helps build owner confidence, makes the project more insurable. It's also becoming increasingly vital for actually achieving and maintaining rigorous performance certifications like Passive House or health-focused standards like WELL or Green Star, which often require ongoing documentation of specific environmental conditions and indoor air quality parameters. Plus, that real-world performance data provides an invaluable feedback loop for designers and builders, helping them refine and improve their future designs and construction methods based on what actually works.
And the restoration professionals. We talked about how their process is changing, but what's the core value proposition for their business in adopting this tech?
Right. As we discussed, a huge part is the significantly increased efficiency and profitability that comes from remote monitoring. It cuts down on costly on-site labor and travel, frees up technicians, lets them handle more jobs. But perhaps the biggest long-term value proposition is the enhanced credibility and professionalism that comes from providing objective, data-driven documentation for every job. It streamlines insurance claims, drastically reduces disputes with clients or insurers, and positions them to offer more valuable, higher-margin services. Things like post-remediation monitoring contracts or even integrating into building-wide proactive maintenance programs. Their competitive advantage really shifts towards being seen as a tech-forward data expert, not just a cleanup crew.
Okay, and finally, let's bring it home to the building owners and the homeowners, the people who ultimately pay the bills and live or work in these spaces. What's in it for them?
For the owner, whether it's a huge commercial portfolio or just your own family home, it's fundamentally about protecting what is likely a massive financial investment. It's also about ensuring a healthy environment and ultimately getting genuine peace of mind. This technology acts as an early warning system. It can prevent a small, hidden leak from turning into a catastrophic flood that causes tens, maybe hundreds of thousands of dollars in damage, disrupts lives, and significantly decreases property value.
And that health aspect we talked about earlier is obviously a huge direct benefit for occupants.
Absolutely. Preventing the damp conditions that allow mold and bacteria to grow means a healthier indoor environment. It reduces the risk of respiratory illnesses, allergies, especially for children or elderly family members or anyone vulnerable. That's a fundamental benefit to well-being that's hard to put a price tag on.
And the peace of mind factor.
Yeah, just knowing that the hidden spaces within your walls, the places you can't see, are being monitored. Knowing you'll get an alert on your phone if a potential problem is detected, that's incredibly valuable. It removes that background anxiety about the silent threat. And finally, it can actually save money on ongoing operational costs, particularly energy bills. Remember, a dry building is a more energy-efficient building. Preventing insulation from getting wet and losing its R value stops that hidden energy drain and helps keep utility costs down.
So looking ahead now, where do the sources suggest this is all headed? What's the future trajectory for these intelligent, moisture-aware buildings?
Well, the overarching vision presented is one of increasing integration and intelligence. The future seems to be about breaking down the traditional silos that exist between different building systems. So moisture data won't just live on its own. It'll be integrated not just with the HVAC system, but with energy management platforms, water conservation systems, indoor air quality monitoring, real-time weather forecast data, maybe even information from the local utility grid about energy prices or demand response events.
Wow. So it's not just about detecting a leak anymore, but potentially managing the entire water cycle, both around and within the building, more intelligently.
Precisely. You could see truly integrated water management systems emerging. Things like smart rainwater harvesting that optimizes collection based on forecasts, advanced siphonic drainage systems that react proactively to predicted heavy rainfall, automated shutoff valves that trigger based on subtle anomaly detection across multiple sensors, even integrating with landscape irrigation systems using soil moisture sensors to optimize water use outdoors based on conditions inside and out.
It sounds like the building itself becomes more like a responsive organism, as one of the sources described it.
That's the powerful concept, yeah. The idea of buildings that can learn, adapt, and optimize their own performance in real time, optimizing for occupant health, comfort, energy efficiency, and overall resilience. Using AI maybe to predict occupant behavior patterns and adjust heating or lighting accordingly, shifting energy use based on grid prices or the availability of on-site renewables, dynamically adjusting ventilation rates based on real-time IAQ sensor readings room by room.
And that must fundamentally change the job description for someone managing a building, right?
Completely. It shifts the role away from just overseeing discrete mechanical and electrical systems towards managing a much more dynamic, integrated entity. An entity that constantly interacts with its external environment, the weather, the grid, and its internal conditions. It's going to require a new skill set, much more focused on data analysis, system integration, understanding algorithms, and holistic optimization rather than just fixing broken parts.
Okay. So bringing this all together then, synthesizing everything we've discussed from this deep dive,
Yeah.
what's the overarching recommendation? What's the main takeaway?
I think the core conclusion coming from all the sources is pretty undeniable. The necessary shift from a predominantly reactive approach to moisture management towards a proactive, data-driven, technology-enabled one. It's not really optional anymore. It's becoming a fundamental necessity. It's driven by the sheer complexity of modern building designs and materials, and amplified by the escalating challenges posed by climate change. The old ways of just waiting for problems to appear are simply becoming inadequate and too costly.
And the sources seem to offer some pretty clear guidance for the different players involved in the building ecosystem.
Yes, they generally have specific calls to action tailored to different roles. For facility managers, it's about embracing these proactive monitoring technologies, learning how to build the business case for the ROI that goes beyond just avoided repair costs, thinking about uptime, energy, health, integrating different data streams, and really moving towards predictive condition-based operations. For designers and builders, the key is to integrate a moisture risk strategy right from the earliest stages of design. Use advanced modeling tools like hygrothermal analysis, pay meticulous attention to detailing and executing the control layers, air, water, vapor, during construction, and seriously consider specifying embedded sensors for high-risk assemblies like mass timber or very high-performance envelopes. For the restoration professionals, it's about investing in the necessary technology and training for their teams, fully adopting scientific principles like psychrometry and leveraging remote monitoring, and transitioning their business model towards offering more sophisticated, data-driven verification and potentially preventative services. And for building and homeowners, the message is to start recognizing that investing in moisture monitoring isn't just an expense, it's an investment in protecting the asset's value and ensuring occupant health. Ask architects, builders, and managers about their moisture management strategies. Prioritize systems that offer early warning capabilities.
And the technology to actually do all this, it exists right now. It's not science fiction.
It absolutely exists. This isn't future tech we're talking about for the most part. It's available today.
Yeah.
The sensors, the IoT platforms, the AI analytics tools that are here. The primary barrier isn't really technological feasibility anymore. It's more about education, awareness, and maybe overcoming some initial cost perceptions or inertia. Disseminating this knowledge about the scale of the threat and the power of the available solutions is really urgent and essential if we want to create buildings that are truly healthy, durable, sustainable, and resilient for the future we're facing.
Okay, so let's just sit with this for a final moment. We've journeyed through the often invisible threat of moisture lurking within our modern, supposedly super efficient buildings. We've uncovered the truly immense costs, not just financial, but significant human health impacts too. And we've seen how technology is offering these revolutionary proactive solutions that really benefit everyone involved, from the initial design right through to the people living and working inside.
Yeah, and it really leaves us with a final, maybe provocative thought for you, the listener, to consider. Look around at the walls, the ceilings, the floors of the building you're in right now. What's happening in that hidden world within those structures? Is it silently managing this pervasive threat, or is there potentially a clock ticking somewhere on future damage and its consequences? How might understanding this science, understanding the technology that's now available, change how you think about the places where you live, where you work, or the properties you might manage?
Definitely a lot to think about. Thank you so much for joining us for this deep dive into moisture science, smart monitoring, and the future of resilient buildings.